I'm Urvi. I am architect from India. I head the workshops at ZEP University, located in the western part of the country. I also have my own design company called Craft Quest. I would rather move on to the session and the speakers of the evening, starting from.
Okay,
We
we'll
can.
go first.
Yes, please.
Okay. Hello, everyone. This is Muhammad Al Abbasi. I'm a PhD student at the University of Liverpool. The topic is about assessing the effectivity of additive manufacturing techniques for the production of building components, implementing innovation for housing construction in Saudi Arabia. So the main motivation of this research is the housing shortage in Saudi Arabia. The current housing ownership is 24%. There is a huge governmental effort to increase this housing ownership as part of the country's vision 2030. So the key factors behind this housing shortage include the rapid growing population. In addition to the current construction method of using framed reinforced concrete structure, which goes along the construction duration, and in addition, there is a lack of workforce, and which increase the overall the cost of the construction. So the aim of this paper is to find out what is the best way to adapt the 3D concrete printing technologies to the current Saudi construction setting. The research questions include first, what large-scale additive manufacturing technologies are available and how can they be used in housing construction? Second, what is the most effective way of implementing additive manufacturing technology in housing construction? The third question, what construction materials and restrictions must be taken into account to achieve an appropriate design within the Saudi climatic and socio-political context? So the methodology of this research relies on assessing the best practice, the best available practice of using 3D concrete printing in the market and find a way to adapt them in the current Saudi construction code. So we have analyzed 7 case studies. The first case study is the 3D Saudi 2040 unit, which has been built by CYB company in Saudi Arabia. The second case study was Dubai Municipality, which was built by Apis Core company. The third case study, the apartments building in Shanghai by Winsan company. Fourth case study, the bod by Cobot company in Copenhagen. And fifth case study is a research showcase known as Comprint 3D in Netherlands. Case study number 6 is printing by a team of mobile robots, which held by the Singapore Center for 3D Printing. The last case study is the mini builders by IAC in Barcelona. So the key findings of this paper were summarized and compared in this table. The table categorized each technique that's used in the case studies based on the printing. Like, for example, it has been divided to 5 categories. The first one, mobile robotic arm. Second one, static robotic arm, the gantry-based system, and the customized robotic, and the swarm robotics. So this table shows the advantages and limitations of each one and their ability to work in harsh environment like Saudi Arabia. And it is possible to implement them in other similar climatic and socio-political contexts. So the conclusion, using robotic arm can increase the production efficiency and also reduce the labor in the construction site. It will also increase the production accuracy and quality. As the final step of this research, we proposed a small manufacturing unit based on a shipping container. So this unit can be transported to construction site for in situ construction. So that's pretty much it. And thank you for listening.
Presentation,
Thank
Mohammed.
you.
I think the second speaker of the session is not yet here, so I would request Rana El Daba to please go ahead with your presentation on digitally encoded wood. Please.
Okay, good afternoon, everyone. I'm Rana Daba, Assistant Professor at the Arab Academy for Science and Technology, presenting the paper Digitally Encoded Wood, 4D Printing of Hygroscopic Actuators for Architecture Responsive Skin, on behalf of Salim and Professor Sharif Abdel Mohsen. Natural wood is known by its hygroscopic properties, in which its mechanical properties and its ability to absorb water differs according to the direction of wood cut and the grain orientations. In this paper, we'll be focusing on the encoding wood motion using printed wood instead of natural wood. Experiments were made to compare between the natural beech wood and the 3D printed wood with 80% plastic and 20% wooden filaments. This showed the ability to control the direction of printed wood as responsive actuators. Angle of curvature of the samples were analyzed using software called Kinovia. In each experiment, we used 3 identical samples, and the average of angle of curvature was recorded. 3 tracker points were annotated on each sample, resembling the start point, the end point, and the midpoint, and the angle of curvature lies between them. The angle of curvature was recorded at the highest deflection value. The research is divided into 2 parts, the physical and digital interface. The physical part mainly requires testing the ability to encode the 4D printed embedded parameters of wood, specifically the grain orientation and infill heights. And its effect on its passive motion, while the digital interface mainly requires measuring the angle of curvature to evaluate and track the passive motion response using Kinovia. Three grain orientations were tested. We printed the first one was the parallel grain orientation with 0 degree grains. The second one was a zigzag straight lines, and the last one was concentric straight lines. The results showed that the highest deflection value was mainly in the parallel lines, with 167 angle of curvature, followed by the zigzag straight line, and finally the concentric straight lines, which shows a very slight motion but with a double curved surface. Comparing these angles to the natural wooden sample, it was shown that the grain orientation with the parallel lines should the most have the same behavior as the wood motion, the natural wood motion, but with lower angle of curvatures, while the other two cannot be compared to the natural wood as it's not actually found in nature. So this gave us the ability to control, to make new grain orientation and control different morphologies, passive motion morphologies. The infill heights we tested was 0.3 millimeters and 0.6 millimeter with different design configurations. The thickness and the infill height of 0.3 shows the ability to have a main hinge position, while the 0.6 thickness show a slightly difference in actuation, or almost a flat surface. This showed that in the 4D or the 4D printing of the wood had the ability to have different thicknesses resembling in the infill heights in the same sample, instead of having, as in the natural wood samples, only one thickness of wood. The contribution of this research lies in introducing additional control hygroscopic parameters such as the printed grain orientation and infill heights to be set as to the established hygroscopic parameters. The paper mainly utilized 4D printed wooden actuators in adaptive facade as passive motion mechanisms that respond to the variation in humidity levels with zero energy consumption. For the future, research and the limitation will be implementing the reduced 4D printed parameters as responsive hinges in full scale and adaptive facade shading and shading devices. These newly introduced parameters are still required to be analyzed in terms of hygroscopic motion grammars to allow for tracking, documenting, and programming the effect of each parameter on motion morphologies. And still further investigation required testing with filaments with higher percentage of wood than the plastic to simulate the same natural wood behavior. Well, the limitation mainly lies in printing thickness that is equivalent to the natural wood veneer, where samples that were less than 0.3 millimeters were very fragile. And finally, the authors are grateful for the support provided by Bartlett Fund for Science and Engineering research collaboration in supporting this research project, Soft Adaptive Building Skin for Energy Efficient Architecture, in collaboration between Princeton University and American University in Canada. Thank you.
Thank you very much. That was a quick run through your research, and it's really interesting. I think we will take questions in the discussion down the line. So probably it's best to go ahead with your comment on from immersive to physical sketches.
Hi, everyone. We are here from Montreal, Munem and myself. So I'm sharing now the screen. So from immersive to physical sketches, a new 3D representation mode during ideation. So when you sketch in VR, in virtual reality, we can sketch in 3D. This is very important because in this paper, we are going from these immersive 3D sketches to these print physical 3D sketches. Could you please close the audio? There is a micro open. And we are doing that automatically without the need of 3D modeling. So in the current ideation process, we are going from 2D sketches to 3D modeling, and then we get the fabrication. This is a very time-consuming process. We have to master the perspective to this sketch. We have to master the 3D modeling. Then we have to model in a way to be waterproof. Then when we are going from sketches to 3D printing, we are translating, 2D sketches to 3D shapes, and this could be challenging. So when you sketch in VR, there is several ways. For example, with Gravity Sketch, you can do the mid-air sketching, so you sketch in the air, but it's very spontaneous, it's very rapid, but you don't need to master the perspective, but you don't feel, it's difficult to feel the sketch going through your hands. And with this kind of sketches, we are not talking about 3D lines, but 3D pipes. We use the Hive 3D that is with the 3D cursor. You can sketch using the tablet that is controlled in SysDOF. And then you have 3D sketches from orthogonal views because you change the position of the tablet. And you feel the sketch because you are using a pen. And so you don't need to master the perspective because you are sketching orthogonal views and you see the 3D shapes. So we propose a technique going from sketches to 3D printing. And we start with, for example, different objects like a mask structure to be placed inside the mask to allow more breathing. So we scan the face, we 3D sketch the lines, Then with some grasshopper definition, we optimize these 3D vectors to be controlling the number of points. And then the second step is converting these lines to closed solid pipes. And then there is a process of sliding and sending the G code to the 3D printer. So what happens? So we get a sketch mask very quick that is freehand and is from the ideation process. There is no 3D modeling included. So the conclusion is, we are printing wireframe objects to explore 3D volumes. So this is very different than solid mockups. We are drawing 3D shapes, but without any 3D printing techniques because it's automatically. Pipe are good for printing, but are not good for 3D sketching. And in the future work, we start doing a part of a car life size, but is very time consuming with traditional printers. So we are working to have a robot arm with an extruder to print that car life size. The car, I have it here, is a way to see. Sometimes we believe it's an augmented reality, but it's in fact a 3D print sketch. Something else that I want to share before going there. So this is the kind of 3D sketches. So these sketches were printed like this, as you see my picture. And this is the way you sketch. So you place the plane and then you sketch, for example, like this. Okay, it's not sharing that. Okay. So that's it. Thank you very much. I was sharing the screen from another software. I see now the screen. Okay. So there is a delay. Thank you.
Thank you, Thomas, for the presentation. And I think it's really moving from one medium to the other, in the sense that yes, 3D printing is very well known now, but this is a very innovative and a different angle I came across as well. I would now invite Ali Ibrahim for the next presentation on augmentive passive actuation of hygromorphic skins in the desert climate. Ali,
Okay.
please go ahead with your presentation.
Yeah. Hello, everybody. This is Ali Magdi. I will present a research paper entitled Augmenting Passive Actuation of Hygroscopic or Hygromorphic Skins in Desert Climates on behalf of me, Ziad Ali, and Dr. Sharif Murad Abdul Mohsen. The aim of this research paper is to introduce mechanisms and focus on an adaptive mechanisms of the adaptive skin, inspired and developed by Cerny-Devil lizard skins in the desert climates, and mimicking its skin capillarity to absorb and retain moisture. Also utilizing hygroscopic properties of natural material like wood, developed and inspired also by pine cones as a natural plant and natural substance. Also, these responses variation are kept to develop passive actuation of a programmable material for the programmable and adaptive skins. It also discusses programmable materials based on physical, experimental, and computational simulation. Hygroscopic properties is known as the material ability to absorb the moisture and to transform during the changing in the levels of humidity from the surrounding environment. And also this process in mood mimics the motions of swelling and shrinking. due to its behavior of food using moisture-driven mechanisms to change form. Also, the gradual opening and closing of pine cones takes place, for example, due to changes in relative humidity in the surrounding. The control of food responsive behavior conducted through physical experiment and simulation, and this directly impact the microscopic design parameters like the grain orientation, type of food, sample thickness, dimension ratio, and other parameters. These parameters also typically affect the response speed and the motion type, like bending, twisting, and folding. This part, we will introduce the adaptive mechanisms developed by the Thorny double lizard skin, while inspiring from the microstructure surface properties of these lizard skins, which absorbs the maximum percentage of the humidity from the surrounding and retains this humidity for a long time using its capillarity sensing, which directly will affect the absorption process that enhance the hygroscopic-based passive actuation systems. 2D and 3D Voronoi cells of this skin, also creating shaded area forming these smallest channels, which called capillarity channels, which are simply the moisture between these scales to accumulate the water. In the experiment, the two laminated materials selected for the testing were silica gel and potassium chloride, and also the third one was a single layer of peach. The process and steps of this experiment was initiated by placing these selected layers inside the humidity chamber and applying a specific condition using humidifier and dehumidifier. The first phase of the experiment at the normal temperature of the room temperature and relative humidity of 47%, it was observed that the experiment of silica gel composites acts as a retainer and reacts rapidly to the humidity and the external humidity with the maximum deflection more than the potassium chloride composite and the single layer veneer. And after 3 minutes in the temperature of 25.7 and relative humidity of 47%, also the silica gel reacts rapidly to reach the highest deflection angle or highest deflection magnitude. After 7 minutes, 24.2 degrees Celsius temperature, and while increasing the humidity level to be 84 degrees, the laminated silica gel sample reached its maximum deflection peak point by 52.08 millimeter, while the potassium chloride reaches the maximum deflection with a constant speed gradually of deflection 48.75 and similar to the single layer of peach veneer by 49.76. After 65 minutes and after decreasing the humidity to 57% and temperature by 24.5, it observed that the silica gel sample or laminated sample returned to its normal phase while decreasing the humidity. But the potassium chloride sample retaining the moisture during the decreasing humidity and reached its maximum deflection more than single layer peach veneer and more than also the silica gel sample. After a long time and after decreasing the relative humidity to be 54% and temperature by 24.6 degrees, the silica gel retained to its constant shape, but the potassium chloride sample reversed and bending slowly with a deflection of 22.44, and also the peach layer veneer stayed constant as it is. As an observation, while showing and observed from the 5 phases of the experiment, the first sample, which consists of peach wood veneer, silica gel, and insulation layer, reacts rapidly to the humidity and reached its highest deflection with the highest speed upon increasing the humidity, and also it returned to its initial state upon decreasing the humidity. while the second sample, which consists of beetroot veneer, potassium chloride, and insulation layer, reacts normally to humidity and shifted gradually, but it returned moisture for a long time, and it can maintain a specific bending mechanism for at least 60 minutes in cases. Comparing these two samples to the base case sample of beetroot veneer, you can control the regulations of a certain bending mechanism. You can maintain morphological transformation during a time duration, and also you can reach bending mechanism with the highest degree of motion. For future work, it will focus on including wider range of experiments and samples, and also under different cases like time of intervals and humidity levels and temperature condition for both composites to address the result of morphological transformation using wood veneer parameters to catalyze the active motion. As a prototype, Grasshopper 3D and Rhino 3D used two module and to model a unit for an adaptive bending skin using and mimicking from a tiny level lasered skin. And also it will be created through 3D modeling and 3D fabricating techniques. So the composite or the sample will be consist of humidity channel as a capillarity, fabricated wood samples, potassium chloride, and wood veneer. As a conclusion, the research aimed to develop the skin morphologies, utilizing programmable passive actuation towards enhancing building facade and adaptive skins. Hygromorphic materials like wood, it can exhibit various deformation patterns, morphologies based on several embedded and controls parameters like wood type, thickness, dimensional proportion, and others. Also, the study in paper will augment these passive actuation mechanisms by mimicking properties of water retention of thermal level skins. Also, the study introduced two laminated composites with the chemical properties like silica gel and potassium chloride. Findings confirmed that the silica gel composite acts as a retainer with the highest deflection with the speed values and different speed values, while the potassium chloride laminated composite demonstrates and the ability to retain fixed morphologies for a long time duration. Resulting of that, you can find a programmable passive actuation with more controlled and regulated actuation of hygromorphic materials for the adaptive systems for the adaptive skins. Thanks.
Thank you for your presentation once again. And with this, we would go ahead with the questions. And I see nobody has posted any questions as yet. But I have a few questions for the speakers. Thomas, you have presented a very interesting way of looking at 3D printing completely. And it's really revolutionary if you are able to print your sketches as wireframe. I was wondering, what kind of printers do you use?
Thank you. The traditional FDM printers, so the traditional small printers, we were able to print this in a piece, but that the limitation is when we see that we can pass from this ideation sketch to be life size. So, of course, in order to get inside the car, so we want to use a robotic car. So now we are talking with some professors, some labs around the world to be printing this car life size. Yes, the car will take time to be printed, but depending on the technique, you know, that sketch now is the slice where, you know, every layer was printed, but we could imagine to be printing the sketch directly in 3D.
Exactly my question, because 3D printing, all the traditional methods and the FDM printers, to print something like this as a wireframe, you would have a lot to post process.
Exactly.
Because I believe
So that's why
you would have to do a lot of supports and
yes, here the support, eventually Munem can answer, but the support were not too much because since you see the ledgers, but that was easy to clean up this model. But of course, we are looking to print in the 3D. What is happening? What is happening is if the 3D printer have to deal with the 3D components that are already printed, and this has to be, investigated correctly.
No, I mean, it's impressive to imagine that you can print your sketch directly, and it, I think, starts with the very little 3D printing pens as a very crude example of it. But
it's not the same, because in the 3D printer pen, you don't have the control. Okay, here you can recognize which car we are talking about.
Absolutely. I meant that the idea of printing in your sketch or your drawing, or to visualize something in 3D, of course, there is a big difference. But what I mean that is the freedom of thinking.
Exactly.
It really opens up the door for the freedom of thinking, that you is the medium which allows you to think freely. That's the idea.
And also to don't be confronted by the limitation of the 3D modeling, because when you want to 3D print something, you have to 3D modeling first. In this case, you are printing your sketches that are freehand, that are and spontaneous, that are immersive in the case of VR.
Yes, but I would also look forward to the idea that you take it further, that you are able to print with a robotic arm, because then you really don't have to process your elements, and it's much faster.
Exactly, but we don't have that in our university. But
you will do it by collaborating with someone else soon, I think.
But we were exploring
all the best
to use the wireframe to be putting some components only to be exploring. But this is only the beginning that we did with Munem. Munem is here. Maybe you want to say something, Munem?
I can speak in Arabic. If there's a question in Arabic, I'm here to speak in Arabic.
Okay.
Nice to meet you, and nice to work with Thomas in this project. It's a very interesting adventure, I think. فيكم تسألوا بالعربي لو سمحوا، لو بتحبوا. اخواننا اللي يتكلموا بالعربي، اذا تحبوا تتكلموا بالعربي تسالوا سؤال بالعربي تفضلوا. No? Okay.
Urbi is not talking Arabic.
I have no clue what is being talked about, so I'm waiting.
Me neither.
I say can speak in Arabic if
can I
question in Arabic.
Any question in Arabic?
May I take next question, please? This is for Rana on her research.
Yes.
The question for you is that, did you and your group try to calculate the impact of the findings on solar performance yet?
Yes, we had tried doing it for checking how much the shading devices will work, but not on the 3D printing part. We have been trying it on natural woods, And so since we're now moving to a new approach for us, which is the 4D printing part of wood, we didn't still do it in terms of finding the solar radiation performance. But for natural wood, yes, it works, and it gives different variation of percentage of shaded area according to the temperature or to the humidity.
I have one more question for you, once again related to the printing, because you've mentioned that you're printing 80% of wood and 20% of plastic to make this
Now
composite
it's
of
20% wood and 80% plastic.
20% wood and
Yes,
80% plastic.
yes.
Oh,
That's why there was a variation in the natural wood, and now we're trying to get the 40% filament. We used it now. It gives better performance. But actually, in market, the maximum types of wood filaments, it only has, I think, 40 or 50% wood, and the rest is plastic. Yeah.
and it's all. So you're considering to take the filament available in the market, or you are also researching on pushing the boundaries of the composite as a material to be printed to increase the performance of your
No,
facade.
no, we're still searching how to advance this part because this is a limitation, and we're still searching how can we integrate it with different types of materials to enhance this part. Yeah.
Yeah, because I mean, 20% wood, 80% plastic would make it, or it may just fall in the zone of questioning: is it really wood or plastic? Or I mean, and the available material itself has
Yes.
limitation. Then maybe it would be good in future to see probably that you would have come up with the
Yes.
innovative material as well, where you say, okay, I am going to use 80% of wood and 20% plastic as
I
I
hope.
started.
I discussed them. But that's the drawback. But the best part that now we can control different patterns in the green orientation. So this gives us different morphologies for motion. So that's why we're trying to help this drawback by adding different types of material as aluminum or different percentages of wood.
Yeah, that's a completely new direction where you will start making experiments with different materials and probably recycling different materials. Now, related to this, the question to you, Ali,
Yeah.
because I see some connection between yours and Rana's research, which has to do with the facade
Yeah.
related humidity, and you have used natural veneer in your research.
Yeah. We use
Yeah.
natural materials. Yeah, we use natural material like wood veneer, and also we used chemical composites like silica gel and potassium chloride to retain moisture. So you can retain the moisture for the sample to controlling the adaptability and the changing and the transformation of the sample during the day. So while you can controlling the reaction of the sample to the humidity level in the external environment and condition, now you can control the sample throughout the day for the external skin of the building or adaptive skin.
Mm-hmm. And you have shown briefly in your way forward that how it could be applied. So my question goes further in the to find out that what kind of species of wood useful in the
I didn't listen to that question.
The
No.
question is there any identified wood species or the veneer type, I would say,
Yeah,
the type of wood?
beech wood will, yeah, beech wood, because it reacts to the humidity with a various speed, and you can control the grain orientation, you can control the thicknesses and everything about the sample. But
So,
beech wood,
the beech wood, would it be reacting the same in the different climatic zones, or it is related to one particular country or temperature and humidity combination parameter?
Yes, okay. Beech wood, by an experiment for a samples or different samples of wood types. So beech wood reacted the most with the various speed and various reaction and bending deflection and deflection angle. So we select the beech wood after researching about the best wood or the best wood veneer that reacts to the humidity.
All right.
So yeah, and after that we are controlling how to control and how to react to the humidity, in which type and in which time, and also the type of bending, also like twisting, bending, or twirling.
All right. Thank you. Mohammed, the question for you, moving from the freedom of 3D printing that we have from Thomas to large scale 3D printing that you're proposing for Saudi Arabia. Is there a specific material you are researching on and could propose you and your team a solution in the climatic zone? Or how is it really going forward?
Yeah, it's actually all about concrete because the current Saudi construction code is work based on concrete, like reinforced concrete. So even in my research, we are developing a 3D printed structure with reinforced concrete, because the current issue with 3D printing is the reinforcement. Most of the example of the 3D printing component are reinforced separately or just printing for a showcase without steel reinforcement.
All right, but have you thought about the fiber reinforced concrete or
Yeah, I have thought about it, but
special?
yeah, it's a good solution, but unfortunately in the Saudi code, it cannot be used alone. So we have to use fiber reinforcement with the steel bar or something like that.
Because any time I have come across so far in robotic printing of concrete, it's a special mix of concrete and not really a traditional mix, if I may say that, of concrete. But also it has a lot of chemicals.
Exactly.
It's really a special mix. So have you and your team gone into the details of what materials to be printed?
No,
Or
my focus will be just on the design, not on the material part. So like optimizing the frame structure to be 3D printed. This is my focus.
okay. Okay, and I really appreciate the chart that you've made in your research, which is really I mean, anybody who refers, it's really clear that what kind of robots and what are the parameters against it, which can be tested. And anybody, I think, who would work on the same lines as you are working, or maybe follow your path, it is really a good research or the base for them.
Thank you so much for hearing this.
I think we are ending the session here, and thank you, everyone. We're running like we are once again sorry for joining a bit late,
No
but
problem.
it was really interesting to interact with all of you. And
May
in the
I
end, I
have?
would like to.
Sorry,
Sorry?
may I have a question for Rana Ali?
Yeah, sure.
Oh,
Yeah, sure.
It's a small question. Of course, you are doing biomimicry, okay? So investigating how in nature the material behaves. But now, a good approach is to get inspired from nature but not trying to copy nature, because nature is difficult to be copied. So eventually, I am interested to see this kind of proposition, but applied with other components of the building, like windows, how it protects, how other materials can be combined in the fabrication of the building. So it's not only the material, it's also the components all together.
Yes, that's the large picture we're working on. Yeah.
So that is the difference between biomimicry and bionics.
Yes. We're actually working on this type of facades now, integrated in facades.
Thank you.
Nice.
Nice.
Thank you.
Thank
I
you,
just
Urbi.
want to say one last thing to all of you, that I represent Cadria. So if any of you are presenting there, see you soon. And if not, if you would like to register, the registrations are open still, I think.
Thank you so much.
Okay, thank you so much.
Thank you, everyone.
Bye-bye.
Thank you.
Bye.
Bye-bye. Thank you, everyone, for listening to all of us. Bye-bye.
Bye.